right, ladies and gentlemen, this is the video on phase diagrams. If you are in the period 3 or the period 5 class, you should be watching this. If you're in the period 6-7 class, you can watch this for review. Before I talk about phase diagrams, which is a certain type of graph, there are a few definitions that need to be mentioned, and the first two are on the screen: critical temperature and critical pressure. So we've talked about liquids, we've talked about solids, now we're talking about phase changes between solid to liquid to gas. If you have a liquid, you can alter its boiling point if you change the pressure. This should make sense that if you're at a higher altitude, it's not going to be the same boiling point, because that whole atmospheric pressure, if atmospheric pressure is less, then you need less vapor pressure to get it to boil. And critical temperature sort of hits this point. It says that, what is the highest temperature at which you can have a liquid regardless of the atmospheric pressure. So it's saying no matter what the atmospheric pressure is, whether it's super high or super low, what is the highest temperature at which your substance is still going to be a liquid? And critical pressure goes along with critical temperature, and it says basically, okay, now that we have that temperature, what is the pressure that is associated with that point? That point, the highest temperature at which it can be a liquid, at any pressure, whatever pressure that is, critical pressure, that's what we call that particular pressure. And it should make sense to you that a substance, if it has stronger IMFs or more IMFs, then it is going to have a higher critical temperature. Just like if you have stronger IMFs, you've got something that has a higher boiling point. If you have something that has stronger IMFs, you have a higher critical temperature, because it's going to mean that your substance can exist as a liquid at a higher possible temperature regardless of pressure. Melting point. Melting point is technically determined by the vapor pressure of the solid and liquid. Solids can exert a vapor pressure just like liquids, and melting point is actually defined as when the vapor pressure of the solid is equal to the vapor pressure of the liquid. Now, this definition it's not used as frequently as the definition of boiling point, meaning when the vapor pressure of the liquid is equal to external pressure. But what I do want to point out here is that melting, just like boiling, is also dependent on pressure, that there is a pressure component for melting, just like for boiling. Now, boiling point, just a reminder here that we do have that pressure definition, reached when your vapor pressure is equal to the external atmospheric pressure. That is the definition of boiling point. Whatever temperature that happens at, that's the boiling point. So if you change your external pressure, you are going to change the boiling point, because you've altered when that vapor pressure will be equal to the atmospheric pressure. Now, normal. In chemistry, normal does not mean regular or ordinary or everyday, although I think that you might be able to extrapolate to see how it fits in with that concept. Normal boiling point. The word normal, when it's used in reference to phase changes, refers to a specific pressure and refers to 1 atmosphere. So when we say the normal boiling point of a substance, what we mean is that, while we understand that, yes, boiling point is dependent on when vapor pressure is equal to external pressure, what we're really saying is specifying, well, okay, let's assume that the external pressure is 1 atmosphere. What is the temperature at which that thing boils? That is called the normal boiling point. 100 degrees Celsius is the normal boiling point of water, because that's why we tend to call that the boiling point of water. It's technically not the boiling point, but it is the normal boiling point of water, because that is when water will boil when the external pressure is 1 atmosphere. We also have normal freezing point. You can have a normal sublimation point, and normal always means 1 atmosphere external pressure. A question that can very easily be asked relating to this idea: what is the vapor pressure of a liquid at its normal boiling point? Kind of a trick question, but it's really saying, do you understand the definition of normal, what that means in chemistry, and do you understand the definition of boiling point? Because if I ask you what the vapor pressure of a liquid is at its normal boiling point, Well, boiling point is when the vapor pressure is equal to the atmospheric pressure, and normal means that the atmospheric pressure is 1 atmosphere. So, if the vapor pressure of a liquid has to equal the external pressure, and I just told you that the external pressure is 1 atmosphere, then the vapor pressure of a liquid at its normal boiling point has to be 1 atmosphere by definition. Superheating and supercooling. We understand that when we have a liquid and we heat it up, it will turn into a gas, and when we cool it down, it will turn into a solid. However, sometimes conditions might be such that your liquid heats up too much, meaning the liquid temperature rises beyond the boiling point of the liquid, and it's still a liquid. It hasn't yet turned into a gas. That's called superheating, heating the liquid above the boiling point without it actually becoming a gas. And supercooling is cooling the liquid below its freezing point without it becoming a solid. This is kind of akin to if you have ever been driving down a highway and you're not paying attention to how fast you're going, and all of a sudden you look down and you're going 40 miles an hour over the speed limit. Well, what do? You immediately slow down, hopefully if you're a responsible driver. You immediately slow down so that you're going something a lot closer to the speed limit. This is what happens in superheating. Your liquid heats up too much, and eventually the liquid will quote-unquote realize that, and then its temperature actually drops. The temperature goes back down to the boiling point. The liquid turns into a gas, and then the gas continues to heat up. With supercooling, it's the same idea. You cool your liquid too far down, eventually the liquid will kind of realize this. Temperature will go back up in order to freeze, to turn into a solid, and then the solid's temperature will drop. So this can be sometimes seen in a cooling curve like this. I mean, we're used to seeing these nice flat lines, but what happens with supercooling is that we have the liquid here, and then we have the solid here, and then this is freezing. Right, when that plateau, this is the supercooling. This is the temperature. We've got temp on the y-axis. The liquid has cooled below the freezing point, but it's still a liquid. And it's realistically at that particular point right there, that's when the liquid kind of realizes that it was quote-unquote driving too fast down the highway, and it slows down and it actually freezes. Now, phase diagrams. Heating curves are those things with the plateaus and the line segments. Phase diagrams are something else. Phase diagrams summarize the conditions at which a substance can exist as a solid or a liquid or a gas, meaning not just temperature, but also pressure. And that's the component that's missing from heating curves and cooling curves. They don't have pressure on them. They're just temperature and then either time or energy. Phase diagrams incorporate pressure. They are a plot of temperature versus pressure. Temperature is on the x-axis, pressure is on the y-axis, and it's for a closed system, so it's kind of understood that you've got water that's in a beaker and not just continually evaporating into a room. And they all tend to have a sort of Y shape, which I'll show you on the next slide. The lines are connected essentially in the shape of a Y, and all the points that are on the lines represent a temperature and pressure, right, combo of the two, a set of points at which a phase change occurs. So all of the lines in a phase diagram are giving you a temperature and pressure at which a phase change happens. The critical point will be illustrated on a phase diagram, and the critical point is simply the combination of the critical temperature and the critical pressure, because a phase diagram graphs temperature and pressure. So the critical point is, well, take your critical temperature, take your critical pressure, and you have that particular point, critical point. And triple point, because this thing is shaped like a Y, because we've got all three phases of matter represented on a phase diagram, because it is a phase diagram, there is going to be a single point where all three phases of matter meet. And this is called the triple point. At the triple point, you have all phase changes happening at the same time. Because all of the points on a phase diagram represent temperatures and pressures at which phase changes occur, the triple point is just one point, not a line, is a particular temperature and a particular pressure at which a solid is turning into a liquid, is turning into a gas, which then turns back into the liquid, which then turns back into the solid, which might turn into a gas, which might turn back into the solid, which might turn into a liquid. All phase changes are happening at once, and that's the triple point. So phase diagrams, what do they look like? This is a very typical phase diagram. They're all going to have this general Y shape. If you look at the lines, they're kind of in the shape of the Y. Notice we have temperature versus pressure being plotted, temperature on the x-axis, pressure on the y-axis. Because of the Y shape of the lines, we get three distinct regions on the curve: solid, liquid, gas. So the entire area here in this first part are temperatures and pressures at which this substance is a solid. So everything that's in this area, your substance is a solid. Everything that's in this area here around the liquid are temperatures and pressures under which your substance is a liquid. And then this whole area right here, that's a gas. The lines separating these the phases of matter represent phase changes. So your lines are phase changes. In between the solid and the liquid, we have melting and or freezing. So this line right here, this is sometimes called the melting line or the freezing line or the fusion line or any of those words that are used to describe solid to liquid or liquid to solid. D, that is a melting point, or it could be a freezing point. The difference is which direction are you going? Are you heating your substance up, in which case it's a melting point, or are you cooling your substance down, in which case it's a freezing point? But that is a melting point because it's the border between the solid and the liquid. So all the dots there represent the difference between the two. This line right here, this is our vaporization or condensation line. So all of those points represent the temperatures and pressures under which our liquid can turn into a gas. Now notice this line ends. There's a distinct end to the vaporization line, and you'll see that on all phase diagram curves. That's your critical point. So that's the highest temperature at which your substance is going to be a liquid, and then the pressure that's associated with that. Beyond this critical point, like up here, we call that supercritical fluid. Fourth phase of matter. There's no difference anymore between the liquid and the gas. It's sort of blending together. Now, this section. If we move in either this direction or this direction, we're moving directly from the solid phase of matter to the gaseous phase of matter and then back. So that's called the sublimation curve, because all those temperatures and pressures represent when our solid will sublime rather than melt. So point C, that's a sublimation point. That's a temperature and pressure at which the solid sublimes. And then A, the triple point. These three phases of matter will converge in one single point. And at A, you have all phases of matter at the same time, and you have all phase changes occurring at the same time. Now, this only happens at one very particular temperature and pressure. It's not multiple temperatures and pressures, but the triple point is where you get all three happening at once. Just to show you an example, this is the phase diagram of water. We have here 1 atmosphere, so that means normal. So this point right here at 0 degrees Celsius, 1 atmosphere, this is our normal freezing point of water. And this point right here, this is our normal boiling point of water, right? 1 atmosphere, reading that down, this is normal boiling point, normal freezing point, 0 degrees Celsius. And also illustrating that water's triple point, which is right here, occurs at, you need 0.006 atmospheres, which is very, very low. You have to get the pressure extremely low, and only 0.01 degrees Celsius, so it has to be very low, and it has to be at that very specific temperature. But if you get water at that pressure and temperature, you get all three phases of matter at once. Now, this is water. This is the phase diagram for water. This is the phase diagram for carbon dioxide. I'm going to go back. Phase diagram for water. Phase diagram for carbon dioxide. Phase diagram for water, phase diagram for carbon dioxide. What I want to point out is this curve. Water, carbon dioxide. The slope of the fusion curve tells you something very interesting about the substance. Hopefully one of the things that you know about water that's very unique to water is the fact that solid water floats in liquid water, and that is very unusual. Solid water is less dense than liquid water. The phase diagram tells you that. Because if we look at the phase diagram here, as you're increasing the pressure on the y-axis, as you're increasing pressure for water, the phase of matter that becomes more likely to be is actually a liquid, because that's what that curve to the left is saying. As you're increasing pressure, it becomes more likely that your water will become a liquid. Well, as you're increasing pressure on a substance, it moves to its most dense phase of matter, because you're increasing the pressure on it. So you're pushing the particles as close together, and whichever phase of matter gets the particles as close as they can possibly be, i.e. most dense, that's the phase that they will become as you're increasing pressure. So because this line, the fusion line, slants to the left, as you're increasing the pressure, it's saying that it's more likely for our water to become liquid rather than solid, indicating that the liquid phase is the most dense phase of matter, versus carbon dioxide, which has a quote-unquote normal phase diagram with that fusion line leaning to the right. Now this is saying that as we're increasing pressure, it's becoming more and more likely to be a solid. That says that the solid is the most dense phase of matter for CO2. Now, something that I want to point out about CO2, we've got CO2's phase diagram right here, apart from the fact that its solid phase is more dense than its liquid phase. If I were to ask you what the normal boiling point of carbon dioxide is, and you told me minus 78 degrees Celsius, you would be wrong. This is not the normal boiling point. You identified that that's 1 atmosphere, which is what normal means. Good for you. But I asked for boiling point. Boiling point is liquid to gas. And what you might be thinking now is, did Mrs. Julian just ask me a trick question? And what I will now say is, yes, Mrs. Julian just asked you a trick question. There is no normal boiling point for carbon dioxide, because it will not start to boil until we get to 5.2 atmospheres. So this point right here, this is not the normal boiling point. This is what we call the normal sublimation point. I cannot boil carbon dioxide at 1 atmosphere of pressure. It will not happen. It will sublime, in which case, okay, then I can talk about the normal sublimation point. But I can't boil it. I can't boil it until I get to 5.2 atmospheres or higher. So we're just going to kind of go over a few things, have a look at this curve. I'll point out where these items are. First up, the triple point. If I give you a curve, you want to look for the triple point. Where is the triple point? There, that's the triple point, that point right in the middle. Critical pressure. If I ask about critical pressure, you go up to the critical point, which is here. That's the critical point, and then you go over and read that. That would be the critical pressure. 73 atmospheres. The critical temperature, again, we go to the critical point right here, and then we go down what temperature is associated with that. It's 31.1 degrees Celsius, so this is the critical temperature. Where does fusion occur? Well, in order to answer that question, you have to understand that fusion means melting. So we are looking for where melting happens. Melting will happen along this line. So anywhere along that line, I will get fusion. Where vaporization occurs. Okay, vaporization, that's liquid into a gas. So anywhere along that particular line, that's where vaporization occurs. The melting point at 1 atmosphere of pressure. So we go to 1 atmosphere of pressure, we go over, and then we say, oh, doesn't have 1. Because it doesn't melt at 1 atmosphere. It sublimes at 1 atmosphere. So we have to be careful because sometimes I can ask you trick questions. Ha ha ha. The boiling point at 6 atmospheres. Well, if you were asking something about that, erase these lines. Estimating from the curve, what would you do? Okay, say, yes, I know that the scale is wonky on this, but you say, okay, 6 atmospheres. It's asking about boiling, so I'd go to this point, and then I'd read down on whatever that is. That would be the boiling point at 6 atmospheres of pressure. And the critical point, where's the critical point? We had to identify that to answer some of the other questions. That is the critical point right there. So that's phase diagrams. You've got a worksheet on that. Make sure you answer the questions. I do want you to turn it in just so that I can check to see how you're doing with that. And if you have any other questions about phase diagrams, please come in to see me.